So, okay. Okay, so we're recording the workshop tutorial for the ISMB CCB conference, where we will try to explain or to highlight explainable deep learning models for image and sequence classification. Let me introduce the team here. We are today will be 5 instructors. It's me, Panos, Petr, Vlast, David, and Filip. And I also want to thank Katarina, that will not be here today with us, but helped a lot with lots of the material that you're going to see today. We are a team, we're parts of a team at the Central European Institute of Technology in Brno, Czech Republic. And we will all be here for today and tomorrow to present and answer any of your questions or try to help with any issues. If you, in general, during this tutorial, if you have any questions or any comments, you can use the chat, Zoom chat, and that we will monitor it and try to help you either in the chat or at any opportunity to ask your question to the presenter. I've put here on the top right a shortened link for our GitHub page for this tutorial, so all the materials and eventually this presentation will be available there for you to see and to run. Okay, so just a quick overview of our 2 days. I'm going to give a short introduction now. Then today we will have a part on neural networks, how to use neural networks for image recognition, starting from basics and going into convolutional neural networks. And then on the second part today, we're going to have a section about classification of genomic sequences. And generally, we try to have a small break every 1 hour, but we'll see what's a natural point of stopping during, how the presentation flows. On the second day, we're going to go into recurrent neural networks, and the main important part of the tutorial that will be the interpretation of deep neural networks, and finally conclusion. And then we have planned to have some time where you can train your own model, and we can work in smaller groups where we can download the data set and help you train your own model. This will be a kind of optional thing. If you don't want, if you are here just to observe, that's also fine. But we thought it might be nice for you to actually be able to build something of your own at the end. Okay. So the goals of this workshop are to get a practical understanding of deep neural networks. By the end of it, you should be able to train some basic networks. You should be able to deploy a trained model online, and we will touch on the basic ideas of interpretation of deep neural networks. You should be able to understand the basic concepts. We will not be able to go into very deep theoretical understanding. We will not touch much on optimization, which is a big field, and we will not go into very elaborate architectures or training schemes that might be more optimized for your task. And we will, as I said, you will learn how to deploy a trained model online, but we will not show you how to make a whole training server online, which would be a much bigger task. So based on that, I will just very shortly present the tools that we're going to use today. So pretty much everything is on Python, programming language. Python, you should all have some familiarity with it, I believe. We will be using Google Colab, which is an online resource that allows you to run notebooks and gives you some computational resources. Importantly for us, allows you to use a GPU for free. We're going to use TensorFlow and TensorFlow JS, which are the kind of the machine learning libraries for Python, and all the code will be on GitHub, and we will use GitHub pages to host the online this online server, this online model. So here, let's just take a short pause, and we have a small poll for you just to give us an idea. You can answer really quickly if you see it. If you don't see it, it's not a huge problem. How much do you know Python? Have you ever heard of Google Colab? How much do you know about machine learning in general? Just to give us an idea of who we are talking to, and maybe hopefully we can understand a little bit about more about the audience. Okay, so people are answering. Okay, I see most people have answered. So I guess people cannot see the results, but I can just give you a quick overview. So do you know Python? It's like split. I have some knowledge, or I work with it every day. Some few people are beginners. Do you know Google Colab? Never heard of it. Okay, so most people not really, but they know Jupyter Notebook. It's very similar. It's basically similar, very similar idea, only it runs online. And about machine learning, majority of people know basic techniques, and there's like 1/3 that knows how to train a neural network. So okay, so and most people have some case results. Yeah. Okay, so most people have some idea about machine learning, which is nice. Okay, so then for most of you, this might be already known, but I will just very briefly go through the introduction. So what is machine learning is a way to make computer systems that learn from patterns in data without specifically giving them explicit instructions about how to do it. Today, we will be talking almost exclusively about artificial neural networks, which are machine learning tools that are based on the initial idea of copying, roughly copying how biological neurons work. The idea was born in the 50s, but then it has gone through several waves of excitement, and then people writing them off or forgetting about them. Recently, in the past 10 years, there has been a big renewal of interest for artificial neural networks, with the deep neural networks, deep learning being the most important kind of field in artificial neural networks today. So neural networks are built out of. We will talk in depth about, obviously, neural networks, but just as a general idea, they're built from simple building blocks called neurons, and they can be combined. The neurons can be combined in increasingly complicate architectures. Deep neural networks, which we will be talking about today, utilize many layers of neurons to model increasingly complex patterns in data. As a general idea, neural networks are a subfield of machine learning, and deep learning or deep neural networks are a subfield of neural networks. One concept to keep in mind, and we will talk about more at the end, is that by increasing the depth of a neural network, in many ways we kind of incorporate the feature extraction step into the deep neural network, which traditionally with other machine learning techniques was done by an expert. So this type of techniques, I mean, is used all over around us for tasks like natural language processing, translation, video processing, face recognition, self-driving cars, making art, and so on. You probably all know and use these applications daily. But for more for our interest, there has been a boom in papers mentioning deep learning or convolutional neural networks in the past, I would say, 5 years, as you see in PubMed here. And applications range from predicting patterns or specificities of biological molecules in DNA and RNA sequences, lots of medical imaging and classification or identification of patterns in medical imaging, and of course last year's great advance in protein folding done by Google DeepMind using again this type of techniques. So this is a promising field. There's lots more to be learned here, and with this I will finish my introduction, and I will let Petr continue with the next part that has to do with neural networks. Petr, you can, I will stop sharing and you can share your screen.
Okay, thank you, Panos. I hope, yeah, here I am. So I will do the present, good. And we will start with something very, very easy and simple, and we will build on that to the complicated models. Imagine that you are trying to do the simple linear regression. So you have your equation for the linear regression. So your prediction is some measured value x multiplied by some slope m plus some constant intercept bias, whatever you call it, b. And you are trying to choose those two constants to have like nice fit through your data. So what you see on the image is probably some idle fit. If like we choose like the wrong constant m and b, we would get like the line that is not really going through the dots. So we somehow need to measure like whether the fit is good or bad. We need some like number. So this ugly handwritten image is basically like we measure how far is it from the true value, from the idle value, from the predicted value to the true value. We call it error. And as the loss function, we can just sum those values, and we will get some measurement how well our line is fitting the points. Okay, so so generally this is for the line, but we can do it like for whatever else. So the goal is estimate our predictions based on the value of some based on some data. And we have some loss function that is telling us like how well we did. Like it's some kind of a measurement of how much the predicted values differ from the real values. And like in the most easy way, you don't need the neural network, you don't need to be a mathematician, you don't need you need the computer, but you can do it even in Excel. I have here like the example like of some real data. So this is some measurement done on the penguins. So we have the flipper length, how long is the wing, and we have the body mass, and we are trying to predict the body mass from the flipper length. And we can do it by controlling those two constants of the linear model equation. So and you can see the results on the picture. So you know, this is probably the ideal fit, and this is like our current line with those two parameters that we have. So if you got something like that, like and you like nobody would tell you anything about the math, what would you do? You would start to play a bit with it. So the slope seems to be wrong. It seems to be increasing. So let's put like, I don't know, 10 here. Okay. Now the bias seems to be too high. So let's put, sorry, 4,000 here, for example. Okay, much better. So the slope maybe still could be a bit higher. So I don't know, 13, 15. I'm not sure. I'm really doing it on the spot now. The bias is too big. So 2,500, maybe even less. And still the bigger slope than we have at the moment. So let's put here the 20, 25. Now 1,000 here. You know, I'm slightly like meddling with the numbers, and with each iteration, I'm looking like how much fit looks like and correct on it. And in a way, like I'm putting it as like funny examples, like what you can do with the Excel. But in a way, this is exactly like what the neural network is doing it. So now okay. So with a few iteration, I'm getting the fit that is not yet ideal, but it's definitely better than what I used to have here a few moments ago. Okay, somehow I will not continue with it because it's not so important. This is how it works, like as the optimization process. You are setting two parameters, M and B, and like the only difference to what I have done in Excel sheet and what here is being done is that based on the derivation, based on the gradient, you kind of know the optimal way how to change the parameters. So here you can see that you are starting somewhere and you are basically going downhill, like if you want to get some intuition. And as you are going downhill, you can see that on the right-hand side, how the fit is improving. Okay, so still like we are not doing the big math, we are just having some intuition. And now let's start doing some math. So this is the building block of the neural networks. This is the single neuron, or sometimes it's called perceptron. And basically it's the linear regression as you know it from the statistical lectures. You have some inputs, x1 to xm. You have some parameters that here they are being called weights. That's just like that's just the terminology. So axis is what you know. Weights is something that you need to choose. And plus you have one extra parameter that is called bias that is like added to the linear combination. And this is your output. So nothing complicated, something that can in principle be done on an Excel sheet again. Let's make the demo that will be using the actual Python code for the optimization. Now, if you would be so kind and open this, I'll copy it to the chat so it will be easier, or would I? Okay, now I probably can copy it to the chat. Okay, so where do I have the chat window? Here I do. So everyone in the meeting.
Here, now, Petr, I can post it. It's fine.
I have just posted it.
Oh, okay.
So it's you should be in our GitHub repo. So all our demonstration will appear here. Some will be even edited for day 2. So if you can click on the first demonstration.
Peter, you have one window open in the middle, and there's a big gray square. You can remove.
Okay, that's my chat window. So I will close it, and if you can. So you can see this. That's the collab. Maybe if you will be using for the first time, Google will ask for the permission. So as Panos noted, it's basically it's Google's flavor of the Jupyter Notebook. There are some technical differences, like it's made to be more safe than Jupyter Notebook. But for us, the main difference is that Google allow you to like run it on their server for free, and it allow you to even to use GPU, which will be like useful for not for this example that is small and tiny, but for like later demonstration. So I will walk you through the notebook. You can run it with me, or try to change it a bit. Like some later notebooks will be too slow to run, so you will like some trainings is running for 10 minutes or so, so you probably don't want to wait, and we will just walk you through the notebook. But here it's pretty simple. So what I'm doing. In the first cell, for you that are beginners in Python, I'm just importing the library. So TensorFlow is the library for deep learning we will be using. NumPy is the Python library for some numerical vector calculations. And PyPlot is standard library for doing the plots. Okay, so, and when you run it, when you start to run the first cell, the Google will warn you, because this notebook is not authored by Google. The Google is using it mostly to provide his demonstration. So if it's something from the GitHub, it's warning you that it's not Google's notebook, but run it anyway. Okay, I generate some random data to have some random linear regression. So I have some training data. Oh, those are not random. Those are random. So I'm just get some bias, do twice X, and add some normal random noise. So if I do the plot, this is how it looks like, and I'm trying to fit the line through it. How could I do it? So I know that there are 2 parameters. Here I'm calling them W0 and W1. And I'm just telling TensorFlow, okay, this is some variable. There is some value of this variable. I need to start with something. So I put there something. And when I will be doing my prediction, I will just multiply the X by W1 and add W0. Okay. Then another component I need is mean square error. So I'll have my mean square error. And finally, I have to start, like so far we didn't try something, but just to show you like from which value are we starting. Like, okay, this is our initial situation. So we have some plots and we have some prediction that is really, really bad. Okay. And like similarly as we did in the Microsoft in the Excel sheet, we will be iteratively improving our prediction. So there are some new terminology that we need to introduce. First of all is epoch. Epoch is basically meaning going once through the data. So when each of your data point is used once, it's one epoch. So we work iteratively, so we iteratively improving, so we can use one data point even more than one time. So once, it's one epoch. If I'm using, if I'm telling here or setting here that training epochs is 500, that basically means I go through every data point 500 times. Then the second number I'm setting here, it's not even necessary, but I'm doing that. It's learning rate. I've said that we are going the step in the like best direction with the parameters, and learning rate is basically setting like how big is this step. Like it could be smaller, and then our journey will be like slow. It could be like too big, and then we will be jumping all around. So those are like two constant I'm setting here. And yeah, and this is like my training loop. So I do the prediction with the current parameters. I calculate loss. From time to time, I print the loss just to have some like to see how I'm doing. Then this line, without much going into that, is calculate me the gradient. So the all benefit of the TensorFlow is that it's doing you the automatic calculation of the gradients, automatic differentiation. And those two lines is that I am improving my values, my parameters, my weights, W1, W0. So let's now run it. Okay. You can see that it's basically no time because it's small data, simple model. And if we like look how we are doing, so now we are basically perfectly fitting the line. Okay, we can do it as an animation. And I think this is taking some time, so I might like skip it. Or let me see like how much time will it take. Okay, basically it's the same animation that we have seen, how the line is improving as the number of the epochs, basically as number of the loops will go. So I will probably return to the slides, keep that like running. Okay, so just the review slides, because before we will go to more complicated things, is this. So we have the input data, we have some weights, some parameters, and we have neural net or model or however we will call it, that based on the input data and the parameters will output the prediction. We compare the prediction to the reality, to the real values, and we'll get it somehow quantified by the loss function. That's something what we call loss. And then we have optimizer that will tell us how, based on this all, we should update our weights. And we've got the updated weight and get like another iteration. And ideally, like with every iteration, our prediction will get better and better. Okay, so this is really the core. This is like I sometimes feel that this is like much more simpler than like many aspects from the mathematical statistics. It's much more simple than, I don't know, mixed linear model for categorical variables. Like this is nothing too much complicated. Okay, there are two more terms, two more concepts that I need to introduce. So far, we have been working with like one neuron, one perceptron, one building block. But to make it really useful, we need more of them. We need to put them, as the name suggests, into the network. And like this is the classical multi-layer perceptron neural architecture. And so you have some inputs that they're in the input layer, and then every next layer, the neurons have inputs all the neurons from the like previous layers. So I don't know, this neuron is having 3 inputs from the input layer, and its output is then input for all the neuron in the next layer. And then at the very end, we are getting the output layer, and this is like giving us the predictions. This architecture, like this type of the layers, is always also called dense layer, and by dense means that the like every neuron is connected to all neuron from the previous layer. So that's one concept that we need. The second concept is like all what I have been doing so far is taking the linear combination. And like mathematicians between you might suggest, oh, but that's not really needed, because like if I'm doing the linear combination of a linear combination, it's still the linear combination. So why do I need like different layers and so on? And the answer is because we will add non-linearity to the output of every neuron. That way we will like stop having only the linear combinations, and we are able to approximate like much broader set of functions. So the beginning of what I have on my slides, it's totally the same as before. So I have the neuron that is basically the linear combination of the inputs, but as the output, I am not taking just that, but I will add something that is called activation function, and this is adding the nonlinearity. The simplest one is, okay, if the output value of this linear combination is negative, I will do 0, and if it's positive, I will do identity. I will just take the x. And that's all what is in it. That's not the only activation function that is being used, but it's the simplest, it's the fastest, and it's being used more and more. Okay, so let's do some examples when we will test it, or maybe before I will go into the example, I will ask, are there any questions, Vlasta or Panos, on the forum that I should answer?
No, nothing right now. I think you can go ahead.
Could I go to the example? Like, feel free to stop me, or if I forget to tell something that will be needed later, Vlasta, then feel free to interrupt me. Okay, so this is the classical data set. It's a very old one. It's about the handwritten digits. So we have 70,000 handwritten digits. Each digit is on a grid 28 to 28 points, so some grayscale. We obviously have 10 classes because we have 10 digits, 0, 1, 2, 3 to 9. So what neural network we will be using for that? So first of all, how we will represent the data. So we will like take the figure, and like it's 28 to 28, so totally 728 pixels. So we will like unwind them into like one big row into the input layer. That's what we have. We will have one hidden layer. We can test like different number of the neurons to put here. It doesn't really matter because the task is very simple. So I believe we will be doing 500 of them, but I have tested it with like much lower number, and it works well. It's dense layer, so everything is connected to everything. And then we will have the output layer that will be, 10 neurons, because we have 10 possible digits. And, we will start with some, we don't know what to take as the parameters. And here we can guess on some like simple, simple graph. So what we will do is that we will set the weights randomly. So initially we will get like very bad fit, very bad predictions. but it doesn't matter. Like we will get some like numbers here, and we will compare it to the true label, true value, which I don't know, could be 6. So if it's 6, we would like to have like the big value in the neuron 6 and small values everywhere else. And we will do some like another nonlinearity, another activation that is called softmax. And like it's basically taking the exponential value here and divided it by the sum of the exponential value. Basically, it's the transformation from like some real numbers to something that is between 0 and 1 and then sum to 1. So we will get some numbers, and after softmax, you will get numbers that will sum to 1, so they can kind of be interpreted as the probabilities. And yeah, and that's basically all what we need. And then like iteratively, we are improving and get better. Again, we have the collab to show it. So if I now open like the second collab here, the menist.ipnb. Okay, so you can see that this is slightly more complicated than it was before. So the good thing is we don't have to like really download the data, because the menist is so classical data set that it's part of TensorFlow, it's part of Keras. So the data are basically being loaded by this line, and they're coming like they're already split into like 2 parts, the train part and the test part. And you might ask why, and the reason is we will talk more about it later, but to say it in one sentence, you don't want to measure the accuracy and loss function on the train data, because it would be too optimistic. It would be like already like it has like it has been trained on those data, so it could be like overfitted. It could be fit the data too well. Okay, so again, the warning, current anyway. So this will just show how the data look like. So this is just one of those digits. You can see that the label is 0, and yes, we clearly see 0. If I will take, I don't know, another one. Okay, this is 3. Okay, now my data is currently oriented like that. It's that it's like the shape is here, so you can see the shape is basically the size of the array. So we have 3-dimensional array that is in the training set that is 60,028, and we want to take this image and make like one big row of 700, I don't know how many values. So so this is how to do it. We basically reshape the array, and we want all the values to be between 0 and 1 for some like numerical reasons. So we divided everything by 225. Okay, so you now see that the training set is 2-dimensional array, 60,000 to 784. We have the labels. The true value is 10 classes. So you can see that if the class is if the digit is 2, it can be also recorded as like the vector of 10 numbers, zeros and ones, when the 1 is only on the position that is corresponding to this value. So it's 0, 1, 2. 2 position is 1. Everything is 0. Okay. Okay, this is again something similar. We can like, this is just like, it's always good before training the model to look on some random sample of the data. Like you can see that this 5 is far from like what you would see in the textbooks, but it's doing fine. And now let's define the model. And I believe that that is something what TensorFlow has really like very nice. So we are taking, okay, the model is sequential, which basically means, okay, we will have the layers. In the first layer will be 500. Oh, so I have even two hidden layers here. So I have 512 and I have this is my input. The input is given by how many pixels do I have. This is my second hidden layer, and this is my like output layer, and you can see that activation now is not ReLU, is softmax. So the ReLU is like either 0 or identity, and softmax is this transformation that will put something between 0 and 1. I can do summary on such a model, which is telling me like how many parameters, how many weights do I need to estimate for each layer. So totally, you are estimating almost 600,000 values. And here will be like fitting it. So we have like, those are the training pictures after transformation. This is like what we expect to have like the labels. We have 5 epochs. That means each data point is seen 5 times. And this is something that I haven't yet talked about, and we'll talk about that later. But basically, we will not get the improvement of the parameters of the weights after like one data point, line one figure, but we'll put them together into something that is called batch, and we'll do like the improvement after each batch. So here I'm setting the batch size 128. If I will run it, okay, you can see that it's running pretty good. It's reporting you the loss, that is some kind of entropy, if I remember correctly. And it's also giving you the accuracy, which basically means like how many times do you guess the correct digit. So this is loss function. This is what is really being used on the optimization, and this is called the metric. This is basically like some statistics that is being calculated on it. So this is on the training set, and we can like now calculate it on the test set, and you can see that like accuracy on the test set is slightly lower than on the training set. That's pretty much typical. Okay, so I will let this be. And now, you know, I remember that I was showing that to my daughter that is 12 years old, and she was asking like, and why do you need like just 500 neurons in the hidden layer? Like would 100 do much worse job? And we have been testing it and like playing with it, and like I believe finally we were doing good with just one hidden layer and 5 neurons in this layer. So it's like you can always, if you will have time, you can experiment with it and see like how the choice of the hidden layer and the choice of neuron and the choice of batch size and things like that will like influence how well are we doing. Okay, so let's go back. So before I'll let Vlasta to speak here about like more complicated topic, I want to repeat something what we have seen in the Colab notebook, and that is that usually when we are fitting the neural network, we are not using like the full data set for everything, but we will split the data into the training set that we will use for the training and test set that we will use for like the final final estimate like of the accuracy and loss function and everything. Quite often, if you are like working in the iterations, you split even the training set like to the part that you actually use for training, and the validation set, which is like, you know, you're looking after every iteration, how well are you doing on the validation set. Okay, so to review just this part, we have been talking about the basically you need three parts for the neural network. You need the data, you need the model, and you need to specify the learning process. The data, you need some critical amount. You need typically a lot of them, and we do the train test valid split, so we don't evaluate on the training part of the data. The model is...
There's a question that I think you might want to answer.
Sure.
What's the difference between validation and testing set?
That's a very good question, and it's, you know, if I go back here, it's not even like sometimes we are using just training set and testing set. I will tell you what's the dangers. The danger is if you are trying not 2 models, but you are trying 1,000 models. You are, you know, you're competing on the Kaggle, and every day you will improve. You have some idea or 10 ideas how you can improve your model, and like every time you will like measure the performance of the model on the testing set. And if you will do it, if you try very hard, it will end up like wrong, because it's called that you overfit the testing set. You basically you like randomly get the models that will be doing good on the testing set, but it's not the behavior of the data, it's just like by random luck. And if I will now bring the new data, your model will not be doing well on those new data. And on Kaggle, I remember that somebody told me that's pretty common mistake of the beginners, that they like try so hard that they do well on one data set, but it will not then generalized on the like new data. So from the practical point of view, testing set is something that you will at the very beginning of the process keep apart, and you will not touch it until the very end. It's usually like not being like touch during the fitting of the network. While validation set is something that you are using during the training process, and usually like monitor how well is your accuracy doing. Is it enough, or do you want to add something, Panos?
It's clear to me. Yeah, I think it's fine. Yeah.
Yeah. Okay, it's telling me that I forget to plug my my network into the power cord, so sorry for that. And okay, so just what we have learned. We have learned about the data, train, test, validation, split. We have the model, parameters, weights. Basically, it's telling you how to get from the input to the output. For the learning part, we have learned about the epoch. That is like how many times do you go through every data point. And like with each iteration, we are trying to minimize some loss function. And regarding the architecture, we have start from very basic, doing like one neuron, linear combination. Then we add the non-linearity. That's what's the activation function. Then we learn how to like put the neurons into the layers. We have learned the dense layer. And now the Vlasta will continue with even like more interesting architectures. And that's probably everything from me.
And I think we still have a pause incoming, right?
We will have the polls incoming, but we will do it probably after the break because I don't have it prepared right now. So let's now do like 10-minute break.
All right, so now you should see everything good, right?
Yep.
All right, so let's continue with the neural networks. And let's say we have an image data set, right? And we, what Petr in a few minutes ago did, he basically took the image data set with the handwritten digits, and he used the dense network to classify the images into the numbers, either whether the network would think it's like number 2, number 4, or something like that. But this kind of network has a few problems with image processing, and we will go over them, and we will see what we can do with it. So first of all, if we take the image and we spread it out in the first layer, let's say we have image by 10 by 10 by 10 pixels, we would spread it out into 100 different numbers, right? So we would have basically a connection from each of the 100 pixels to each of the neurons in the next hidden layer. And what can happen is when you have images, for example, 1000 by 1000 pixels, then you already have a million numbers and like multiple million weights you have to train, which can be, it can be a little daunting and a little too slow for the computer. Sometimes you could train for maybe a few days before you could get some results. So that's one problem. We would have too many parameters if you would use the dense layer for our image problems. Another big problem is when we look at the images at the bottom of this slide, we see basically the same image, right? We see a cat and a cat. But if you look closely, the cat on the left side is a little bit shifted to the right, right? So this cat is in this image is in a little different position than this cat. And the dense neural network doesn't know it. It just looks at these individual pixels. And if we train the network to see cats or to recognize cats, it would basically just look in this place, and it would be unable to recognize the very same cat in just like a little different position, which is not ideal if we want to classify images, right? And part of this problem is there is no proximity. So the dense network only looks at the image like a bunch of pixels, basically. It has no idea whether one pixel is closer to the other. So you can see the dense networks are, if we actually had some more complex data set than a little handwritten, little handwritten digits, it would not work. So we will introduce something that's going to help us. And that one thing is called convolutional neural network. And to fully understand what is convolutional neural network, we first have to look into the convolution operation. So what you need to know is when we have an image like this, we can apply so-called filter to this image. And filter is something like this little matrix. It's basically a bunch of numbers that we can slide over the image, and it's going to give us some result. In this case, we have this image of dog, right? Grayscale image of dog. And when we apply this filter to the image, we're going to get this result on the right. And when we take another filter, let's say this one on the bottom, we're going to get this image. And you see these images are different. And what is the idea of the filter is it's going to basically look for some kind of a pattern in the image. So let's say this pattern, when you look at it, and when you look at the result, when we apply the filter to the image, we're going to see it's highlighting the vertical lines. And if you look at this different filter, it's highlighting horizontal lines. So you can think of a filters basically as a matrices, which if you set them a certain way, they are going to look for certain things in the image. And when you apply it to any image, then it's going to give you basically a heat map where the black pixels are low values and the white pixels are high values. So it's basically telling us, all right, so in these black spots, the pattern is not present, but in these white spots, the pattern is there. On the right side, you can see how we apply the filter. Let's say the green matrix is the image, and the white matrix is the filter sliding over the image. And if we apply this filter to the image, we're gonna get something called a feature map, which is the same as this thing on the right with the black and white pixels, where we have the horizontal lines highlighted. And what would it look like in a computer is basically this pink matrix, which is a bunch of numbers, which the higher they are, the more they are signifying that there is the pattern in the image on that position. So if you look at the pink, let's say on the top left, if this filter is looking for some pattern, on the very top left, there is number 4, which is quite high. So we can say the pattern is present in the top left of the image. And if we look at the middle section, there is a 2. So we can say the pattern is not that much present in the middle of the image, on the middle left. So that's what filters do. They are basically a matrix. When we slide it over the image, it's going to give us a so-called feature map, which is going to tell us how much is the pattern present in the image and on which positions. And what is interesting is we can actually look at these numbers, at the patterns, as parameters. So when we say we want to teach the network something, we can teach it to look for patterns that are important. So let's say we have a data set where we are classifying, let's say, dogs against cats, right? So when we would be training the model on this data set, dogs and cats, it would gradually learn the patterns that are important for dogs and that are important for cats. So for example, for dogs, it would learn some kind of a filter that's going to look for the shape of a dog's head, and the similarly for the cats. And what is important is when we when we apply the filter to the image, we're going to get this feature map, which signifies how much is the filter present in the image. And this is a simple example. This is grayscale, right? So it's just black and white, but we can do the same thing with RGB images. But it's RGB images are not simple matrices. RGB images are RGB, right? They have 3 channels. So they have this channel for a red color, this channel for a green color, and this channel for a blue color. But we can still do the same thing as we did before with the filters. So these smaller matrices down here, this is our one filter. So this one filter basically consists of 3 different matrices. One is looking for something in the red channel, one something for the green, and one is looking for something for the blue. And when we multiply all these matrices, we get some numbers which tell us how much is the pattern in the position. And then we just sum them up, and the output is, again, just a simple 2D matrix with high numbers in the positions where the pattern is present and with low numbers in the positions when the pattern is not. So that's the very key concept which the convolutional neural networks are working with. They are basically just learning these patterns which they should look for. And once they figure out the patterns, they are gonna basically work much better. So let's look how it would look in the model, in the neural network. On the input, we would have something like 10 by 10 by 3 RGB image, right? So 10 by 10 pixels, and times 3 because we have 3 RGB channels. And what we can do, we can not only apply one filter or teach the network one filter, we can do multiple of them, which is reasonable if you think about it. So what we want to do is we usually want to specify how many filters we want the network to learn. So let's say we have this image, and let's say we want the network to use 6 different filters. At the start of the training, they are going to be, of course, random, as always we do with the neural networks. We are starting with random weights. So the filters are going to be random, and then as we train the network, the filters are going to change their values, which are the weights, and they are going to start to look for more relevant patterns. So if we apply these 6 filters to this image, it's going to make it a little smaller. As we've seen before, when we apply this filter to the image, it's going to make the image, a little bit smaller. It's going to produce the feature map that is a little bit smaller than the image. So when we apply it in the neural network, let's say we start with an image that is 10 by 10, we're going to end up with feature maps that are, let's say, 8 by 8. And we will end up with a feature map for every filter we used. So let's say we have the first filter, it's going to look for the patterns, and it's going to produce this single feature map, 8 by 8. Then we take the second filter, and it's going to apply and produce us another feature map. So that's going to be another layer and another and another. And what we're going to end up is basically image at 8 by 8 by 6. And the 6 is the same number as our filters. So basically for each filter, we're going to get another channel, another feature map. And what is usually done is we just don't stop there. We apply another convolution layer. And this is where we can get a little bit unintuitive, but what you can basically do is in the second part of the network, we can start doing the convolutions again. But this time, when we are looking with the filter for the patterns, we are not only looking into one feature map, but we are looking into all of them at once. So it's similar as we did with the RGB. With RGB, we basically had 3 different feature maps, red, green, and blue. And we applied 6 filters, and we ended up with 6 feature maps. And to those, the filters are going to look into all of them, and each filter is going to produce its own feature map. And it's going to make the image, again, a little bit smaller. So it goes from 8 to 8 to 6 by 6. And then we will have 10 feature maps because we had 10 different filters. So here you can see you can actually choose the number of filters the neural network is going to learn. It's similar to when you would be choosing the number of neurons in the hidden layers. You can basically experiment how many filters are important or how many filters are needed for the network to learn. And this one paper did this experiment. We're gonna look into this. They basically trained the network on a big data set of images, and they started looking to the actual filters to figure out what did the network learn. And what they find is the network starts to learn a simple patterns in layer 1, like simple, maybe some lines, maybe some vertical lines, horizontal lines. And another layer, it's going to make combinations of these. So it's going to make it into maybe some complex patterns, maybe some circles, moon shapes. And then as we go up and up with the convolutional layers, the network is going to make more complex and complex patterns. So at the end of the network, you can basically have a filter that's going to tell you where in the image you can find, for example, here you can see a dog face, which is interesting. This is very important insight into networks because you can actually see what is it looking for and on which information is it deciding on. Another great addition to these convolutions, it's something called pooling layer, which is a standard addition to the convolutional networks. So the very basic building block is the convolution layer, right, which produces us the filter maps. And we are kind of making the network learn quite a lot with only a few parameters, because one filter takes only, well, let's say it's a filter 3 by 3. And it's only gonna take us 3 by 3 means nine numbers, which is 9 weights. So for a single filter, we would just have 9 weights, which is a lot less than, let's say, like some kind of million connections when we would be using the simple neural network with the dense layer. But still, even if we have this little number of weights, we can still make the computations faster and more efficient. And we can do it with the so-called pooling layer, which is very simple. We have this feature map, which is the result of applying the filter to the image. And what we can do is we will basically look at some area and take the maximum number, which corresponds to basically just taking the most significant patterns out of the whole feature map. So we end up with basically somehow aggregated or somehow simplified feature map. And this is making the network to learn a bit faster because we have less computations to go through, because we are basically making the feature maps a little bit smaller in a smart way. So we're taking the maximum of them. And on the right side, you can see how easy to compute it. It's basically just the similar thing as the features, similar thing as the filters, but we are just basically taking the maximum number out of these four. So that's the pooling layer that's going to make our computations a little bit faster and a little bit better. And at the end of the network, we will have something like these feature maps, and we will still have to somehow decide to how do we decide what is on the image, right? Well, we have to classify the image into something. If we image something like cats versus dogs, we still have to decide which features are important, or on which we will decide to classify whether it's dog or cat. So what we do is we take the feature map or multiple feature maps at the end, and we will do something called flattening, which is basically just taking all the pixels and making them into one array. Basically the same thing as the simple network did at the very beginning, but we are doing it at the very end of the network, where we don't have the pixel values, but the numbers mean how much is some pattern in the image. So we can actually see there is some very strong pattern in the left middle of the image, right? And then we will just flatten it out, and we can then join it with a dense layer, which is gonna learn from these informations. We're gonna look at it in this little example. So let's say we have a task, and we want to give it a photo, and we want to decide whether it's a car or whether it's a face. So we will feed it the image. We will give it to the convolutional layer with two filters. And each of those two filters is going to give us a feature map. So let's say the first filter is looking for a wheel, right? So when we say car, we think maybe it's going to have a wheel. So the first filter is going to learn it should look for a wheel. So when we give it face, it's going to output 0, 0, 0, 0, because there's no wheel on the image. The second filter can look for something like eyes, let's say. And when it's looking for eyes, it's going to output something like 1, 1, 0, 0, because we have two eyes, one on the top left and one on the top right. Then we have these feature maps, right, which tell us whether is there eye and where, and whether is there a wheel and where. And when we do the flattening, we just basically concat them and just spread them out. And then we will do this layer and this classification layer with softmax, right, with the probabilities. And we will do dense connections. So every neuron from this layer would be connected to the neuron in the last layer. And then the network could learn which combinations mean which things, right? So for example, if we give it face, it's probably going to have strong weights in these positions, because when we have eye in the top left and eye in the top right, it could learn something like, all right, so if there's eyes in the top left and in the top right, it's probably going to be a face. So it's going to learn to have high weights in these positions, so it can signify a face. So that's a simple example how you can think about basically the convolutional neural networks. What are they doing inside? Of course, when we learn the network with some data set, we have no idea which filters is the network going to learn. It can look for something absolutely and totally different than we can think about. So let's say it would have, faces versus cars. And for us, okay, so it would make sense to look for eyes and for wheels, right? Because face is probably not gonna have wheels on it. But the network could look for something completely different and still work. So that's why it's important to kind of visualize the filters or visualize something where is the network looking for, because then you can, as we said, have optimistic performance on the training set. But then if you apply it to new real-world images, it can go it can go very wrong sometimes. So let's look at the architecture. Again, the typical convolutional network architecture would be something like this. We have image, we apply filters to it, we get the feature maps. Then once we get the feature maps, we will do the pooling layer, which will make them a little bit smaller, but still the same 6 feature maps, just a little bit smaller. And then we can repeat the convolutional pooling as many times as we like. And then at the very end, we will do flatten. We will spread out all the feature maps, and we will do dense layers, which can make combinations of these features. All right, so now let's go again to the GitHub, and we will look at how to.
Can I just relay a question from the chat that asks, basically the main idea is how to choose how many filters to use in each layer, or
yeah.
Like if you just give a
quick, I understand. Yep, definitely. All right, so the question is how many filters should we choose, right? And that's a similar question on how many neurons you want to have in your hidden layers. And the unsatisfying answer is, of course, it depends. But usually what you start with is something like, maybe 30, maybe 60, maybe 100 filters. And then you find out how the network works. If it's going to learn well, if it's not going to learn well, and then you can adjust the number of filters. It really depends on your data set, because some data sets, you can basically just apply 5 or 6 filters and it's going to be enough. But for some data sets that let's say they have like maybe 10,000 different labels, like images where you have to recognize one of 10,000 different labels, there you would have much larger number of filters because the network would need them. So the answer is it really depends on your data set. Usually you start with a smaller number, and then you can gradually maybe increase it, and then you will see how the network behaves based on the testing score, on the validation score.
And sorry, another question is if there are standard filters, or are they usually initialized as random numbers? And I think,
yeah. So yeah. So we initialize all the filters with random numbers right here. But it's actually a good idea to have some kind of standardized filters, right? Because the images, the images have kind of a similar patterns all around, right? If you look at, for example, some edges, maybe some circular things, some colors maybe, and that's a very good idea to have something like standardized filters. And we're gonna look into that just right after this simple CNN notebook. So that's a very good idea, and we're gonna look into that one. But first, we're gonna just do the random ones. So what you can do is go to the GitHub and you can open the CNN demo notebook. Just a note, you can just open it, or you can just leave it closed. You can just watch me go through the notebook, and it's just totally fine. You don't have to run it yourself. But if you open it, you can actually play with it a little bit and try out different things. So if that's something you want to try to do, feel free to do it. So I will open open the notebook.
Vlasta, you're not sharing your screen right now. You need to share your screen again.
Oh, that's okay. Yep. So now I'm sharing, right?
Yeah, you're good.
Yeah, I'm good. Okay. All right, so let's look at this notebook and let's look what we can do with the convolutional networks. So what we're gonna do is we're gonna classify so-called CIFAR-10 dataset, which is dataset, a very simple dataset which contains images of various things. Let's just look at it. Let's say this is one of the images. This is image of a frog. It's a very low resolution, but this is the dataset we have. So we have to try to work with that. And we have these very low resolution images, and this one is a frog. And we have 10 different labels. So we can have image of a bird, image of an automobile, image of a dog, and stuff like that. So we're going to try to have this dataset and learn the network to correctly recognize these classes. So we are lucky because we don't have to download the dataset in a complicated way. The TensorFlow library actually contains a few datasets we can use. So if you want to just try to teach some kind of a neural network, you can just go to TensorFlow and you can check out all the datasets they have there, and you can load them in a very simple way. Just call datasets. We want the CIFAR dataset, and call load data, and what you're gonna get is train and test split, which is very convenient if you just want to make some prototype models. So we have train and test, right? We also want to have some validation, so we can monitor our model during the training, not just at the very end. So we're gonna take the train images and we're gonna take 5,000 of them and we're gonna leave them for the validation. Now, what we also have to do is we have to normalize the images. So the images, as you look at them, RGB images, they have values between 0 and 225, right? That's the RGB values. But the neural network, they don't like these values. Neural networks like standardized or normalized values at their input, ideally between 0 and 1 or somewhere in that range. Because if you had two large numbers, the network can still learn, but it's gonna be much harder on the network. So usually it's a good idea to somehow pre-process your images, and the most simple way is basically just divide everything by 225, which is taking the numbers from 0 to 225, the pixel values, and just gonna squash them between 0 and 1. So that's what we're doing here. It's very important, so you remember this when you are working with networks. It's always you have to pre-process the data in a way that the network basically is able to work with. So let's look at the splits. We will have 45,000 training, 5,000 validation, 10,000 test. That's fine. If we check out the pixel values, we can see they are normalized, right? They are between 0 and 1, so that's what we want. We have this image of a frog. It's telling us it's label 6, and we don't want label 6. We want to have it something more human readable. So what you can do is you can go to the CIFAR website. What I did, I just basically made a dictionary, which is going to translate out the labels. So we're going to see that 6 equals to frog. So we have these 10 labels, and we will try to classify them. And so at this point, we have our data ready, right? We have our training split, we have our validation split, we have our testing split. And what we also did, we divided the numbers by 225, the numbers of the pixels. So we have our images standardized between 0 and 1. So we can say we have the data ready for the neural network training at this point. So now we move to do a definition of the model. So right now, this is where we define the convolutional neural network. And this is also the place where you define the number of filters, right? That's what the question was about. So let's first go over the definition. So we define, a model does sequential, which means we want to have basically layers in the network that go one after each other. You're gonna use this start every time. Basically, you're never gonna use anything else than sequential with these basic neural networks. And then we will start adding layers to it. So after the input, we will add convolutional layer, right? We will take the image, we will take convolutional layer, and then we will specify details of this layer. So in the first convolutional layer, let's say we want to have 32 filters, and that's an arbitrary number, right? We don't want to do something like 1 million because then the training would take ages. But starting with something, you know, about 30, maybe 10 to 100, maybe that's going to work, and we'll see. And we can adjust it later. Usually, when you develop some kind of model, you will adjust the number of filters, maybe number of layers, you know, gradually, depending on how you do on the validation set. So these are the filters, the number of filters. Kernel size specifies how big are the filters. So what we are doing is we are making filters of 3 by 3, which means each filter has 9 weights, right? So 3 by 3. And here you could also do something crazy. You cannot do bigger filter than image, obviously, but you can do, you know, something like maybe if you have images 1000 by 1000 pixels, you could do filters like maybe 100 by 100. But what researchers found is usually a good idea to have kernel sizes of or filter sizes of 3 by 3 or 5 by 5, because usually that's enough. Usually when you have these filters and you have enough layers, the network is going to make combinations of these and find the more complex patterns anyway. So the standard is having filters of 3 by 3 or 5 by 5. We will also have, you know, activation ReLU inside the network, right? And softmax at the end. But let's go to the beginning again. We have convolutional layer, then we will have the max pooling, right? Making the filter maps a little bit smaller, so the computations are faster. And then we can do it over again. We can make convolutional layer, you know, maybe we will add a little more filters here, do the pooling again, do the convolutions again with even more filters. And once we have this convolution, we can do the flattening. So on this image, we can see we are not doing the pooling at the very last convolution, which we could. It's totally fine to do it. It's totally fine if you don't want to. And what we will do, we will basically spread the pixels, right? That's the flattening. That's the FC on the image. And then we will just add some dense layer at the end. We will make combinations. And the very last layer is going to be 10 units because we have 10 different classes. And we're going to change the activation function. We're not going to have ReLU anymore. We're going to have softmax. So it's going to output us the probabilities of the 10 different classes. So that's the model definition. Very simple, just convolutional layers, max pooling layers. It's basically the same thing as you see on the image, just, you know, maybe a different number of filters and maybe without the pooling at the end. And when we define this model, we can call something called model.summary, which is a function of TensorFlow. This is basically going to tell you how the network looks in a more detail. For example, this is our first convolutional layer. It's gonna take 32 by 32 images, and it's gonna output 30 by 30, right? Remember how the filters made the image a little bit smaller, so that's why we have 30 and 30. And the last dimension is 32 because we have 32 filters, right? And this now at the beginning, that's just a batch size. We don't have to worry about that right now. This is the stuff you would expect her to be. And what is interesting, you can actually look at the parameters, how many weights you have that are gonna train. So that's it. And now we have the data set. We're gonna talk a bit about the batches. So you heard about the batch size, and there were some questions in the chat like, what is the batch size, how big it should be, right? And stuff like that. So let's touch a little bit on that. So what we are doing with the neural networks, we are not giving it one image at a time to improve on it. We are giving it a couple of images, and we are telling it to improve on all of them at the same time, and then we're going to move the weights. So what this means is we're going to tell it, okay, so here's 10 images. You're going to predict all 10 of them. We're going to find out how you should move the weights. So you improve each one of them, or you improve this and this. And then what you do is you basically average the changes in the weights. So let's explain that a little bit better. You give it one image, and it's gonna have this gradient, or the direction in which it would move the weights to be better at that image. But before you actually move the weights, you're gonna do this for 10 different images. So you're gonna basically have this direction of where you want to move to improve on the first image, where you want to improve on the second image, and then once you have all 10 of them, you're gonna average them and move the weight in the direction that's gonna, in average, make these 10 images better. It's gonna maybe the weight is gonna do a little worse on one of the images, but because we are averaging it, it's gonna do better on 9 of them. So it's basically, you are basically teaching the model to learn something from multiple images at the same time. And what you could do is you could basically give it the whole data set, right? So we could do, okay, so predict me, you figure out how to improve on the whole data set, and you're gonna move in that direction. So that's what people used to do in the very, very old school days, but they quickly find out that's not that doesn't work that well, and it's also extremely slow. Because if you would have to compute the step of the weights for the whole data set, it's going to take a long time. And it's also not going to work very well. It could work well, but it doesn't always. So what they did is they basically started to split the data set into batches. And this does two things. One, it's making the computations much faster, right? And second, it's actually making the model work a little bit better. And the reason for that is when we make this batch out, let's say we have data set of 60 images, and we split it into 10 different, or into six different batches of size 10. Each of these batches is gonna, let's say it's gonna approximate how the data set looks, but it's not gonna have all the data. So the model is basically trying to, always do a little bit better on a good approximation of the data set, but not the whole data set. And experimentally, people find out that this actually makes the model behave much better. So that's the reason why we are splitting the data set into batches. One, it's gonna the model is gonna learn better, and second, it's gonna be much faster for us to train the model. And so that's all about batch size. So we remember, we defined our model here, and now we are going to train the model. So what we do, we just compile the model. We're gonna tell it, stuff like what's our loss function, like how you should compare your prediction to the label. But most importantly, we have to call the fit function, right? So we're gonna fit the training data. And here we can actually specify two things. We can specify the epochs, which is, remember, the number of times you go through the whole data set. And we can also specify the batch size, which is these little groups of data, which you hope it's gonna kind of approximate the data set, and then the model is gonna gradually learn one batch after other. So now we call the fit. We call the fit on the training data, and the model is going to train for a little while. And you can see this is the accuracy. Here you can see the training accuracy. And when we have 10 labels, if the model would behave absolutely randomly, it will have accuracy of 10%, right? Because we have 10 labels, and it's going to randomly select one, so it should work in like 10% of the time. And once we train the model, we can see the testing accuracy goes from 10 and 44 into something like 83. So that's the testing accuracy. But what we are more interested in is the validation accuracy, right? Like how does the model do on the data it's not being trained on? We want the model to be able to recognize new images, not only the images it was trained on. So that's what the validation set is for. And we're going to have this validation accuracy here. That's the thing you want to go up. That's the most important number. Or not the most. The testing accuracy is the most important. But when you are fiddling with the numbers, when you are trying different batch size, maybe different number of filters in the network, you want to observe how is your validation accuracy changing, and that's going to give you a rough idea how the model generalizes to new data. So we can see the model goes from 50, maybe 10 at the beginning, then 50, and it goes something like 72% validation accuracy, which is not bad, but definitely not something amazing. But we can see the model is learning how to recognize some of these 10 different classes. The automobile, the frog, the horse, and stuff like that. So we can basically say it's going to recognize 7 out of 10 correctly. And what the only thing we did is had some data, had some convolutional model called our fit, and then we can see it's actually doing something. It's not doing it like 100%, but it's doing it not randomly, which is good. When you are training this kind of model, what you can do is you can basically train, basically plot your accuracies. So this is the x-axis is the number of epochs, right? So this is how for long we've been training, and the y-axis is the accuracy. So we want to go up, and we can see the training accuracy goes up, and the validation accuracy, maybe goes up, and then kind of stays in the 70% range basically. And that's something we want to go up, right? So sometimes we will in a few minutes we're going to talk about like how to actually make the validation accuracy go up with the training as much as possible, because we don't want the model to just be good on the training data. We want to be good on the validation data too. And as we were talking about the number of filters, the batch size, you can actually also tune with the number of epochs you are training for, right? So for example, now we were training for 10 epochs, but it's not a given that we want to have 10 epochs. Sometimes models are trained for 5 epochs. Sometimes the model are trained for thousands of epochs. It really depends on your data set, and it really depends, on this graph. If you see the training goes up, and up, and the validation, maybe stays or even goes down, then that's a good sign of that you are training basically too much. You are overfitting the model to the training data, and then it's not going to be good on the validation data. So you may want to consider, stopping your model at some point or not training indefinitely. And now here we have a good example. Let's say this is the analogy of our model on 1,000 epochs. This is on 100 epochs, and this is something like 1 epoch. So this is not exactly correct, right? Because more epochs doesn't exactly correspond to better model. But you definitely want to train for multiple epochs. 1 epoch is not enough usually, unless your data set is crazy big. Usually you want to go over the data set, a couple of times. Then once we done, let's say we have tuned the network a little bit, we have changed the number of epochs, we have maybe reduced the number of filters or added more filters, we can then go and evaluate the model on the testing data set, which is like our very final evaluation to see like how are we actually doing on the whole new data. Because if you would only use the validation data set, with the validation data set, you are still, kind of fiddling with the number of neurons, with the batch size. And what you can do, you can accidentally make some combination that's very good on the validation data set, but it would not be good in practice. So that's why we have the test set. So at the very end, we can actually do like actual evaluation. And here we have 71% accuracy on the 10 classes. And as we always talked about, the filters, what you can, I have this code here. You don't have to worry about it. But what it does is basically, we can look at the image and inspect the network in a smart way, and we can find out on which part of the image is the network focusing on. So let's say we have this image, right? We have the frog, and we feed it through this network, and we look at how the network behaves. And what it's going to give us is this basically heat map, a saliency map, which is going to have red values in the areas which the network pays the most attention to. Basically, the network decides on this area. Because of this area, it's a frog. So this is just a little sneak peek on the interpretation of the convolutional networks. We're gonna look into the interpretation much more tomorrow. This is just a little sneak peek how you could maybe get a better idea what your model does. All right, so that was the simple convolutional neural network. Do we have some questions?
We have a lot of very good questions, and maybe some of them we are trying to answer them in the chat, but it's so many of them, and some of them are really good. So I will start with a few of them that I like, and you can try to understand them. Like one of them that I have trouble to answer honestly is, do the batches stay the same like across the epochs, or are they randomly chosen for each epoch?
Yeah, that's a good question. So remember how we split the data set into the batches, right? We had the data set, and we basically split it into 6 or maybe 1,000 different groups. And this split, it's usually done is you shuffle the data, and then you make the batches. So you basically have like random images in each of the batches. And what this does, it basically what was found out, it's when you shuffle it and you then batch it, it's going to make a pretty good approximation of the data set. And once we go through the epochs, what you can do is, what is usually done is you will shuffle the data set again after each epoch. So what you do is basically you have the data, shuffle it, split it into batches, and train it for one epoch. And then what you can do is you can shuffle the data again, split it again, and then train another epoch. So that's the I think that's the best way to do it. You can always you can shuffle the data preemptively and then do the same batches over and over. You could do that. That could also work. But what is a better idea, just to make the model basically give it a little bit more variance in the data, so it just doesn't remember to classify the batches. You can shuffle the data set after each epoch. I think that's a very good idea to do. Yeah, that's the standard thing how you should do things. Yep. So any more questions?
Yeah, another question is about the batch size. Like I have tried partially to answer that, but like, why did you choose batch size 64, and like what are generally rules to
Yeah, so the batch size is that's if you look at Stack Overflow, that's one of the most upvoted deep learning questions. Like, what's the correct batch size? So it usually what you do is you choose something like 64, 128, 256. Like this multiplies of 2, and the reason for that is it doesn't really matter that much if you have like 2, unless your batches is like 5. That's too small. You have like big enough batch to reasonably approximate the data. But what is usually done is you do something like 64 or maybe 256. And why? It's because usually the deep learning models are very very intensive on computations, right? Because if you try to run some of these notebooks and let's say we will have 1,000 epochs, you will find out it's going to take a long time to train them. Sometimes when I was doing my master thesis, my models, I had so many models and I was training them for how much, like maybe even a week. It took a week until everything was trained, so which is a crazy amount of time. So what you do is you put these computations on the graphic card. You basically, usually if you have some kind of neural network, you can train it not only on a processor, but you can train it on GPU. And on GPU, you basically want to be able to fit the whole batch into the GPU at once, so you can parallelize your computations. So that's why usually there are multiplies of 2 on the batch size, because the graphic card memory usually have these types of memories which you can fit this amount of data or this amount of bytes. So you can basically try to fiddle with it. You can find out how big your GPU memory is and when you train like some kind of crazy experiment, what you can do is you can basically have as big of a batch size as fits in your graphic card memory. So that's something like that can be your upper limit on the batch size, basically. Okay.
That is probably everything from me. Vlasta or Panos, do you think any other questions should be answered publicly?
I think we can. I think we should move forward a bit because we have a lot to a lot of stuff to go through, and
yeah. I'm just gonna give me 30 seconds. I'm gonna grab a water and I'll be right back.
Sure. Yeah, that's fine. Well, other questions was what does attention mean, which we will cover tomorrow. I'm just looking.
All right.
So one quick question: what's the difference between accuracy and validation accuracy? I guess. I mean, you can answer.
So in the notebook, right, we have accuracy and validation accuracy, and the accuracy which you see there is the training accuracy. They don't put training in front of it, but it's the training accuracy. So, and in general, training accuracy is how good are you doing on the training set, which is the set of data you are training the model on, right? That's the data the model sees. And the validation accuracy is the accuracy on the validation set, which is the set of data the model doesn't see during training. So what we could do is basically if you evaluate the model and it has 100% training accuracy, and you tell someone, you know, my model is amazing, but if you give it a new data, it's not going to work. And then you're gonna ponder why. And that's because the model basically remembered all the data. But if you have a good validation accuracy, you can actually say my model has a good accuracy on data it's never seen before. So that's the difference. All right. So feel free to post more questions into the chat. Now we're going to do something a little more difficult. And that's a skin cancer classification.
Can I? It's like we just went 1 more hour. So should we do another 5-minute break? Quick 5-minute break.
Yeah, definitely. Yeah, let's do 5 minutes, and I'm just gonna put the time here. So let's meet.
It's 10 past. 10 past. We start again. Okay.
All right.
Yeah.
Okay. Okay, so are there any more questions after the pause, or is it?
No, you can go ahead.
I can go ahead. All right. So, just have my water. Okay, so now we've seen this, you know, cats and airplanes data set. That's not really interesting, and so we're gonna do something more interesting. We're gonna do skin cancer classification. And it's going to be much bigger data set. It's going to be 100,000 images. And our task is going to be classify each of the images into the correct category. So what we need to do is, right, like, again, load the data, pre-process the data, create our architecture, and then train the architecture on that model and evaluate. There is well, it can be easier, but we can actually do, you know, make some of these steps we can let other people do for us. So one of these steps is the model creation, right? So you have been asking, like, how many filters should I use? How many layers should I use? How deep should network be? How many, you know, what should be the size of the filters and stuff like that. And you could fiddle with that yourself, or you could use some of these existing architectures. And these architectures are basically proven to work on a wild variety of datasets, and they have been showcased. They basically made a bunch of papers with these architectures, and they have shown, all right, so this architecture, it can actually learn the correct filters. It can classify images from various different data sets, and it can do well. So we have kind of a good, not a guarantee, but a pretty good idea that they work for image classification. And the good thing is you can actually load them right for TensorFlow, which is what we're gonna do. And this is one part where we could ease our job a little bit. We have these architectures, so we don't have to define our own model. We can just take existing one with random weights. And now we're going to talk a bit about transfer learning, which is something that there was this question, right? Like half an hour ago, which was, why are we are there some kind of standardized filters like what we could use for multiple data sets? And the answer is kinda yes. So that's what we call transfer learning. So the idea is that we're gonna take some model that has been pre-trained on some other data set. So let's say we have this pre-trained architecture we have been looking at, and this architecture could have been pre-trained on some kind of some huge data set, some huge image data set, which basically means the network has learned all kinds of filters that are relevant for different kinds of images. And what the idea of transfer learning is that we're gonna take this model and we're gonna let our data set run through this model, and then we're gonna look at the very last, the feature maps. You remember the feature maps at the very end? We're gonna look at those feature maps. We're gonna flatten them, and then what we're gonna do is we're just gonna train the last dense layer. So we're basically just going to learn what combinations of these patterns are relevant for our data set, and which combination means that there's this kind of skin cancer, or there's this different kind of skin cancer. So that's the idea of transfer learning. We're basically gonna take a model that has been trained on some other data set, and we're gonna assume that the filters the model has learned are relevant even for our data set. And we are just going to train the last layer to basically learn the model how to make the correct combinations of these features. And we're going to predict our data based on that. When we talk about pre-training, usually what we mean is that the model has been, at least for computer vision, for image classification, what we usually mean is the model has been pre-trained on some kind of a huge data set, and one of these data sets is ImageNet. It can be, don't get confused by the name ImageNet, because it's not actually a net, it's not a neural net, it's a data set full of images. And it's crazy how huge it is, because it has 14 million images, and it has over 21,000 categories, which means over 21,000 labels. So in the last layer, you can basically, when we had 10 different digits to classify from, we could have like 1 to 10. Here we have, in the very last layer, we have 21,000 different classes, which is kind of crazy. But the idea is that if we train model on this huge data set, and you can see, the data set has all kinds of images. It has like normal images you could take on holiday, but you can also have like some very detailed images, some maybe even paintings and all kinds of stuff. And so basically the idea is it's going to learn all the kinds of filters that are relevant for different images. And the good thing is we can use this pre-trained model in TensorFlow too. So TensorFlow allows us to use, for one, the architectures, and second, the pre-trained models. So, but you actually need some kind of pre-trained model. You cannot just, choose your architecture and let's say, pre-train the architecture on ImageNet. You could do it, but it's going to take a long time. So we are kind of limited in the selection of the pre-trained models if we don't want to pre-train them ourselves. So the good thing is, if we look at all these, complex architectures, they all have been pre-trained on ImageNet, and we have the option to either take them as they are, like random weights, or we have the option to set the weights to the pre-training. So they basically, the model will be pre-trained on the ImageNet, which is something we're gonna try to do, and we're gonna see how that works with our skin cancer dataset. So let's go over this transfer learning again, because this is one of the most most revolutionary ideas that has been in neural network training. Basically taking some kind of a model, having pre-trained model for some kind of a general task, and then only training a little part of the model at the very end to make use of it. And the reason why it's so useful is because it solves two biggest problems we have in the deep learning. One of them is the time, right? It takes a long time to train the correct filters. It takes a long time to go through the huge data sets and everything. And when we use pre-trained model, we are saving the time of the training the model, and we are basically given the default filters from which then we can make combinations and maybe adjust them a little bit and go from there. So that's the answer for the question that was there for like an hour ago. This transfer learning, you can look at it like kind of having standardized filters. They are not hand defined. They are still learned through the deep learning. They're still learned through the network being trained on some kind of a data set. But you don't have to do the training. You can take the pre-trained model and you can then use it and adjust it to your liking. So the pre-trained model, we take the model, we just cut the last layer because we don't want to be classifying into the 14,000 categories of ImageNet. We want to be classifying into our 7 labels of skin cancer. So what we're gonna do is we are just gonna remove the last layer, remove the weights from that layer, and then we're gonna put our own layer there and connect it to the feature maps at the very end. Then we are going to train the classifier on our skin cancer dataset. And during this training, this is also important, we are not going to train the rest of the model, the pre-trained part. We're going to leave it as it is. The reason for this is we do not want to mess with the basic filters that have been taught, that the model has taught itself from the ImageNet. We just want to be training the very last layer. And once that stops working, we can actually do fine-tuning, which is, we can slowly start to unfreeze the model and slowly start to train, let's say, at first we will just train the very last layer from here. Then once that is not enough for us, we can maybe unfreeze the model to this point and go from here and train this model and the classifier too, like this part. And when that stops working, we can maybe start unfreezing a little bit. But we're gonna look how to do that in code now, how to do the transfer learning on your dataset. So jump to the GitHub again and open the transfer learning notebook. And well, actually, you don't have to do it, right? You can just watch me do it. But if you want to try yourself, feel free to go to the GitHub and run the notebook and see what you do. Maybe you can even improve the results that I have there. So let's jump to the notebook. Okay, so what we're gonna do is we're gonna do the skin cancer dataset, right? And there are 7 classes. We are just going to use 3 of them for simplicity. So we can have maybe a smaller data set that's gonna run a little faster. So what we're gonna do is we're gonna download the data, right? That's the first part. We need to get our data right for the network at the beginning of any deep learning project. So what we do, we have the data in our GitHub. So you can just use this code. You can just download them and then put them into folders. And then we will have, let's see, I will show something interesting, which is very useful feature of TensorFlow, which is creating the data set for you, basically. So let's say we have downloaded the data, and this is amazing thing. When you download the data, you can structure it in this way. This is like the standard way you are structuring classification data sets in deep learning. Is you will look into the dataset folder, and you will have 2 folders or maybe 3 folders, maybe train, validation, and testing. We will not be using testing here, so we just have training and validation. And inside these folders, you will have another folder, 1 folder for each of the classes. And inside these folders, you just have a bunch of images that correspond to this class. And if you have the data in this format, TensorFlow allows you to call this function, image dataset from directory. And you just basically give it the path of the directory. You give it you tell it you want to shuffle the data. You tell it the batch size, and you also tell it the image size, which is as we said, we have to pre-process the image data, right? And for us to be able to feed it to the network, we have to have all the images of the same resolution. You cannot have one image, 1,000 by 3,000 and another 200 by 100. That doesn't work. You will have to resize your images to the same size before you feed it to the neural network. So all of these things, batch size, image size, everything, you can just leave the TensorFlow to do it. You can call image dataset from directory. And if you have the dataset in this format, in these folders, it's going to create you this train dataset that's ready to go for the deep learning model. You can just, put it into the fit function and it's going to work, which is amazing. This is an amazing feature. You don't have to, do all this work yourself. You're just going to call it and it's going to load everything correctly. All right, so that was our dataset creation. If you look at the data, this is how it looks. We have, 3 different, we can only see two classes here, but we have 3 different classes of skin cancer. And this is what we are going to feed to the model. It's gonna have to learn to recognize these types of cancer from each other. So now let's move to we have the data ready, right? That's the first part. And now we will have to create the model. So, what we want to do is we want to create the transfer learning model this time. We will try to do transfer learning on this data set. So we will have this base model, this part that is pre-trained for us. And what we can do is we can just load MobileNet v2 from TensorFlow. That's one of the many different pre-models architectures you can load, which have been proven to work quite well with images. So this is from TensorFlow. TensorFlow contains this architecture. You can load it up. You just tell it how big your images are. We tell it include top equals false. This means we do not want the last classification layer. We don't want the last layer where they are predicting the 14,000 categories. We want the model without the layer, and then we are going to add our own layer, which we're gonna do a little bit later. And this is all good. And we also tell it weights equals ImageNet. And this is the part which tells the TensorFlow, okay, so we want this architecture, but we also want it to be pre-trained on ImageNet. That's the big image data set we were talking about. So this is the parameter where you tell the model, okay, so I don't want random weights. I want to start with my weights being pre-trained on ImageNet. So it's gonna have all the filters already learned from the ImageNet. And because we don't want to be training the whole model, we want to freeze it and only train the last part. We will set the variable of the model, the trainable variable, to false. So that's basically what that's going to do when we call the fit function. It's not going to change any of these weights. If we go summary on this model, you can see it's quite long. It's quite more complex than the models we've been doing so far. But it's still, from the most part, it's still convolutional layers, pooling layers, flatten, maybe some mathematical tricks, but the very core of the model are the convolutional layers. And we can see in the very last layer we have feature maps that have 7 by 7, 7 by 7 features, and we have over 1,000 of these feature maps. So that's cool. What we can do is we can just flatten these and make dense layer after that. So let's join all of these pieces together. We're gonna make again sequential model from Keras, and if you remember, we still didn't normalize our images. We still didn't divide them by 225, and this is something you should do, but this is the exception. When you are training, when you are using pre-trained model, you want to pre-process the images in the same way that they used to pre-process the images for the pre-training, because the model, for example, it was pre-trained on images from -1 to 1, and if you would give it images from 0 to 1, it wouldn't work very well. So it expects to have the images from -1 to 1. That can be some kind of variation of on the pre-processing. Sometimes it's maybe 0 to 1, sometimes it's something different. So when you are using this architecture, what you can do is you don't have to worry too much which pre-processing it used. You can import, where is it? Pre-processing. I don't know exactly. I don't know where is the import exactly, but basically from TensorFlow, you can pre-process input. Blah, blah, blah. Yeah, I cannot find it right now. Maybe you see it, but I'm blind. So basically what you can do is you can call the pre-processing function of the model. So each of these big pre-trained architecture is gonna have its own pre-process input function that's gonna have the correct pre-processing for the images. So what we're gonna do, we're just gonna put it at the very beginning of our model. We call it Keras layers, and first thing you do with the input, you are going to pre-process it. And don't get confused by the layers. It's not like a dense layer. It has no parameters. It's basically just an extra step before we go to the base model. Okay, so don't worry. There's no deep learning here. It's just pre-processing the images before we feed it to the actual model. Then we're going to put the base model, which is the MobileNet model, the big architecture pre-trained. And as we saw, it's going to give us 7 by 7 filter maps with over 1,000 of them. What we're going to do is we're going to max pool them. We're going to do the pooling. Then we are going to flatten them. And then because we have 3 different classes, we're just going to do the dense layer at the end with the softmax activation, right? Because we want the probabilities of the 3 different skin cancers. And that's basically it. This is how you can basically make your own model. You can take a little bit of this base model, you can add your own layers to it, and then you can train that. And remember, the base model is still frozen. We are just going to train this dense layer connected with this base model layer. So again, we're just going to compile the model. We're going to give it the loss function we want. We're going to tell it, hey, tell us the accuracy as you are training. And then we are going to fit the model. So this can, just fitting the model. We are using the data set that the TensorFlow allowed us to create from the folders. And let's say we're going to train it for 10 epochs and see how we do. So we are training for 10 epochs. Then we can just, visualize it. And you can see that it's going up, but the validation accuracy, it's quite a bit behind quite a bit behind the training accuracy. So it looks like the network, it's maybe starts to overfit a little bit, even when we just train the last layer, right? We are just training the last classification layer, and it's still managing to get a training accuracy of almost 100% and validation around about 85. The thing to note here is like we have 3 classes, so if the model would be doing absolutely random things, it would have accuracy of 33%. So we can do it's doing all right. This is just a loss. Usually you can look at the loss and at the accuracy. You want the accuracy to go up and loss to go down. Basically, you can just double check with these both graphs. So this is when we train the classifier, and now we can try to fine tune the model, which is meaning we're gonna unfreeze a few layers and before our classifier, and we're gonna train these. So we're gonna set the base model to trainable, and we're just gonna set all the layers to false again. Like we're gonna freeze all the layers again, except the last about 4. There's 154 in the base layer, in the base model, and we're gonna freeze 150 of them. So we're gonna unfreeze the last 4 layers, and then we're gonna continue the training. So again, we're gonna compile the model, and then we are going to train the model again. The same thing, we're just gonna fit the data set, give it how many epochs we want, and we're gonna continue from the last point we stopped at. So we have the classifier trained, and now we are just going to continue the training. So if we continue to the training, we're gonna plot the metrics, and we can see it kind of, the green line signifies where we started to unfreeze the layers. So you can see, okay, so it kind of got a little bit worse, then it got a little bit better, and now you can see interesting thing, the training accuracy actually goes to almost 100 here, which is a clear sign of something we call overfitting, which means the model is basically, we are telling it to get good on the training data set, and we are hoping it's gonna do good on the validation, right? But the model has so much parameters and so much power, so it's able to actually memorize all the training data. Our data set is not that big. I didn't mention it at the beginning, but the amount of the images we have from the skin cancer data set, it's maybe like 100 of each. So it's not like we have, it's not like we have thousands of images. We have very small data set, which is quite a common thing when you are working with, for example, medical imaging. You don't have that much data. We have a lot of images of cats and dogs, but we don't have much images of, for example, chest X-rays. So this can be a big problem if you are working with some kind of data set which is quite small. What can happen is your model can just remember the data and give you 100% testing, the training accuracy, but your validation accuracy is only around 80, which is not, it's not bad, but it's not close to 100. So what can we do with this? We can actually improve the data set itself. We will do something called image augmentation, and I'm just gonna hop to the slides real quick. And this is a big part that's gonna make your models much better. Maybe not much, but it's gonna help. It's gonna almost always it's gonna help and make the metrics better. So data augmentation is what it means. It's basically we're gonna take our data point, which is, for example, image, which is this little kitten on the left, and what we can do, we can kind of manipulate it a little bit. We can maybe rotate it a little bit. We can maybe zoom. We can maybe translate it to the left a little bit. And what that's gonna do, it's gonna basically it's gonna make our data set bigger. But we still know when we create this new image, we still know it's the same cat, and we still know this is how cat looks like. So it's still a valid new data point. It's still if we take every image of a cat and we rotate it, we're going to have double the images, and each of them is going to be correct. It's the same thing with the MNIST. If you look at the handwritten 8, you can take it and you can kind of deform the image, and it's going to give you a different one, but it's still going to be an 8. And if you train the network on these kind of changes, it's actually going to do, it should do better, because it seems new data points, and you basically created a new data from nothing, which is amazing. That's can very much help your model, because let's say we have very small data set. If we make a few augmentations, if you rotate a little bit, maybe flip the image a little bit, maybe adjust the brightness a little bit, we can have much bigger data set, and you can train the model to look at the same images under different conditions, and you can basically force the model to rely on the important patterns and not just remembering, for example, how the image looks like exactly. You have to be a little bit careful with image augmentations, because, for example, sometimes you can, if you do, let's say you have a driving car, and you are going to flip the training image of a traffic sign that's telling you to go left, and you want the model to be able to recognize it's going left, but you're going to flip it and it's going to point to the right, then it's not going to have a right label. So you have to be careful with the augmentations. You cannot use augmentations that will change your label. You have to choose them carefully. So this is just another example of augmentation. Let's say we have this butterfly, and you can do all these kinds of stuff with it, and it's still going to be an image of butterfly, but you're just gonna make it a little bit harder on the model. You're gonna make it work a bit smarter. All right, so that was augmentation, and let's hope and see how we do the augmentation in the code. This is the wrong one. This is the correct one. So what we can do is, again, Keras, or TensorFlow, I should say, allows us to use pre-built augmentation methods. So what we're going to do is we're going to basically create a little model. Again, this is not going to be a deep learning model. This is just going to be some steps which we apply to the images before we feed it to the actual network. And what we're going to do is we're going to do a random flip, and we're going to do random rotation. And if we apply it to a single image, you can see on the very left, this is the original image, and all these images after it are created from the same image. It's the same image. It's just slightly rotated, slightly changed, slightly maybe flipped horizontally, and this is gonna force our model to recognize the it's not gonna be enough to just remember there's a brown thing here, and that's the important thing. That's the label. When it's going to look at all these different images, it's going to say, okay, so there's no brown. I have to look for something different to classify this correctly. So it's going to force the model to actually generalize better. And this code I have here, it's going to be training the model with the augmentation. So all this code is the very same thing as before. This line is the only thing we have changed. We just edit data augmentations before everything. And we're going to see how that works. And so we're going to make the model, we're going to train it. And when we plot the results, we can actually see the model doesn't overfit anymore. The training accuracy is still better than validation accuracy, but it's not that big of an amount. And if we look at the validation accuracy at the very end, it's actually, maybe 2, maybe 3% better than the validation accuracy without augmentations. So here we can quite clearly see the data augmentation, that was the only thing we changed, and it made our model better on the validation accuracy, and it made our model overfit less, which are great features you want to have with your model. But the thing is, we can actually see from the green line, the fine-tuning didn't help that much, right? Even before, when we unfrozen the pre-trained layers and we started training them, it looks like it's not helping that much. And this is interesting because you would, if you remember the ImageNet dataset, the dataset with 14 million pictures, it didn't look like it had features that would be relevant for skin cancer dataset, right? That's kind of unintuitive. Like how can features from general images be useful for skin cancer detection? But you can still see we can actually classify it with validation accuracy of 83%, which is better than 33. It's not perfect, but this model is very rough, and you could still make a lot of improvements on it. So it's doing something clever, still with the features from the pre-trained model. And if we actually tell to ourselves, okay, so we're gonna adjust the pre-trained features, right? We're gonna unfreeze the model and we're gonna train it. That can work sometimes, and sometimes it can also not. As you see here, we are not improving that much by unfreezing the model. Maybe we have to unfreeze a little bit more. Maybe the unfreezing doesn't really matter because we already have the feature maps we need. And I have also this fine picture here. So usually your custom layers are not that good as this pre-trained. You may not think the dataset was relevant, but it's surprising on how many datasets the ImageNet pre-training actually works. It works for even medical imaging can use features from the dataset. But yeah, it's definitely something you can experiment with, and if you want to make your model really good, then you can go really deep and try to unfreeze the model even more, or even train it yourself from the scratch. All right, so that was transfer learning, and let's recapitulate a little bit. So what we've seen here were the convolutional neural networks, right? These are a bit better for the image, no, actually quite a bit better than the simple dense layer networks, which are called MLP. MLP stands for multi-layer perceptron. That's, you can just think of simple neural network with only dense layers. On the other hand, we have the CNN, the convolutional neural networks, that use convolutions and filters to find patterns in the image, which are using convolution layers, pooling layers, flattening layers, and also the dense layers at the very end. And what are they doing is they are basically taking the image, they are applying the filter or multiple filters, and each of those filters are going to give us the feature map. And then we can make combinations of these and apply filter to these maps and so on. And also, when we are using the pre-trained model, we are freezing the model, we can train the last layer, and then we can gradually unfreeze it if we want to fine-tune it a little bit. And we can just, from TensorFlow, straight away, we can take the pre-trained model, we can train it on our own data set, and hopefully have better results than if we would have to train it for ourselves. All right, so now this is the end of the convolutional neural network part. And we're going to have a little quiz here. So I don't know, Peter, can you put it up?
Definitely. Could we take the questions before that, or would you prefer first?
Yeah, definitely.
The question. So first of all, some of you have realized that there's the missing line in the Colab. We didn't load the pre-processing on the mobile V2. So David did.
So that's why I couldn't find it.
Okay. Yeah. so it should be.
Yeah, that makes sense.
And we do apologize for the things cost. Another there was a question that I believed I know the answer, but I didn't realize that it's slightly more complicated than I thought. The question was, do you do augmentation only on the training set or also on the validation and test set?
Yeah, so that's a very good question. Usually what you do is you definitely augment the training set, and you keep the validation set and the training set as they are, because what you want from validation and testing set, you want to simulate how the model would work in real life. So if you would throw a new data on it, how that would work. So when you are, throwing new data into the model, you are not, you are not rotating it, right? You are just taking it as it is, and you are predicting based on that. So that's it. If you want to augment your testing data, you can, right? You can try to figure out like maybe under which angle the model works the best. But at the end of the day, you would still average the results, right? So
yeah,
it would be similar.
So that's what I found. Like I originally believed that you augment only the training set, but then I have found that exactly as you have said, like people like Jeremy Howard are actually augmenting even the testing set and claiming that like it will.
It's definitely not a standard thing to augment your testing set, but you can do it. You can do it if you think it's gonna tell you a bit more how good is your model. You can do it, but generally during the training there is no point in augmenting the validation set or the testing set. During training, the only thing that matters is the training data and how do you feed it into the network. If you are augmenting the validation and testing set, that's only good for you personally to see, maybe a little bit better or maybe a little bit worse number at the very end when you are measuring the validation accuracy. All right. Any more questions?
Like nothing that I would think that needs to be like answered publicly. So I'm launching the poll if like David or Panos will not stop me.
Yeah, so we're gonna ask you which type of augmentation do you think is not suitable for chest ray dataset. And you can see if I'm still presenting, I think I should be. You can see, how the chest ray looks, and you can vote on what do you think is not a good augmentation.
Vlasta, I have also a question that someone asked to me, like in private message, and the question is that the example showed that you fine-tune from Epoch 10, and the question is why not fine-tune from Epoch 0?
Yeah. So basically, usually this is all usually experimental, right? But the idea behind it is you want to leave the filters as they are, because if you are going to fine tune from Epoch 0, your classification layer is gonna have random weights, right? Because when we add your classification layer on top of the filters, on top of the feature maps at the very end of the pre-trained model, you are going to have random weights there. And if you would unfreeze the pre-trained layers before that, that would basically mean you would have, layers you are training that are kind of reasonable, and right after them, there would be a layer with totally random weights. And this means that this would not be quite optimal for the learning process. So the learning process, how do we find the better parameter, right? The gradient. It's using derivations or partial derivations. It's called, the algorithm is called back propagation. We are not going to go much into depth with it, but if you would have, it would basically mean you would have a very large update in the very last layer, and it can influence the updates in the layer before it. So it would basically start to change the filters in the pre-trained layers too quickly. It would start to learn, maybe nonsensical things because your last layer is still random and it's going to make random predictions. And to make them better, maybe the model is going to tell, I'm going to leave the random layers as they are, and I'm going to change these filters. But in reality, that's not going to be, that's not going to make sense. So the intuition behind it is you want to, kind of slowly train the last layer, kind of make it, settle down a little bit, so the updates are not too big, and that gradually unfreeze the layers, maybe make the learning rate a little bit lower, make the model update really, slowly and carefully, so it doesn't, jump some weight or some filter doesn't jump like, by some very big number at one step, and then you can kind of get lost in the training.
Okay, so I'm ending the poll. I'm not really sure and sharing the results that there's like one correct answer here. It's more like what you believe that that is the problem you are trying to deal with, but I'll let it comment. Vlastimil.
Yeah, so this is this is question where it can be of course a couple of right answers. It depends on the magnitude of the augmentation, but the biggest thing is the most thing that makes the augmentations wrong is the horizontal flip. So that's what the most people answered correctly, 52%. So well done. And the reason is when we look at the image, when you flip the chest ray, it can actually make your heart be on the other side, which is a special type of disease on itself. So when you are classifying diseases, you can actually, the reason is you can change the label of the image by augmenting it this way. So remember, when you are augmenting, you need to make it in a way that's going to keep your label as it is. That's very important. And the other most popular choice was change brightness. And this can be also right, because if you change brightness too much, then you can make the image a little bit maybe very hard to read or some nonsensical. But slight change in brightness can actually help you, because there was this, I think it was from Google. They made some neural network that was classifying chest X-rays, and they found it worked amazingly in one hospital, and then they made the algorithm work in another hospital, and there it wouldn't work at all. And what they found out is the lighting conditions were very different in the new X-ray in the new hospital. So this is why we can use the brightness. We can kind of simulate, different lighting conditions or different devices that are making the X-rays. So you can make the model again, look for the actual look, for the diseases in like any different, all kinds of conditions, not only under one lighting situation, on one type of circumstances, or only one kind of device. Yeah, so that's that's it. I think we can close the poll. And now I believe we have a pause. I believe we have a little 5-minute break.
10 minutes.
Yeah. So we'll see you back at, let's say, 16:08.
Okay.
So we went through several data sets. We've seen penguins right at the beginning, and now we were looking at image data sets. And now we will move into sequence data. So I will present you the data set we will use for our example here. So sequential data are another kind of data types, let's say. They can be anything that is basically a sequence of some characters. So for example, here we will work with a G quadruplex data set. which is a sequence of bases. So the G quadruplex are a stable secondary structure of nucleic acids that occur when quartets of guanines, bases called Gs, are stabilized by a monovalent cation. And they form a characteristic layered structure, as we can see on the image. If you don't understand this, don't worry. I myself am not a biologist, so I see this data set only as a sequence of some DNA, and we are trying to find some structures there. So, simply put, this data set consists some pieces of sequences of characters. So we have a lot of them. We have 300,000 pieces of DNA, and each this training sample or this sample in the data set is 200 characters long. So we have 200 characters of either A, C, T, G, or N in different variations. So N goes for a character that is not, there was maybe some mistake during preparing the data or something like that. And ACTG are our types of bases that can be found in DNA. So, and we will, what we want to do with this data set is that we are trying to tell if these sequences of 200 characters, so for each sequence, we want to classify the sequence and say if it contains a G quadruplex. So we will look at the sequence, and we want our model to tell us, is there some, or does this sequence form a secondary structure that is G quadruplex? And we want the model to say yes or no. So we will have positive and negative samples in the dataset. And since we are dealing with another type of data, we will have a look at how do we want to present this data to the neural network. So it's a bit different than with the images, because our data is this sequence of letters. We cannot just throw it into the network. We have to somehow pre-process it for it, ideally into some kind of numbers that it understands. So what we do first with this genomic data, but we can also do this with natural language and other sequence data. So we cut it into tokens. The process is called tokenization. And important thing is that we need to decide what kind of token do we want to cut our data into. So we can either cut it into single characters. So we would take, in this DNA sequence, we would take A as our first token, C as our second, and so on. Or we can cut it into words, which makes more sense in natural language, so words as we know them, or subwords, which an example in natural language would be prefix, then the root, and then suffix. And these three will be like each separate token. And or we can cut it into k-mers, like we see here at the bottom in the image. We can cut it into groups of 3 characters. And then once this is done, we proceed into numericalization, because these tokens we still cannot just throw into the network like they are. We need to somehow put them into numbers. So we numericize them, which is very simple, is just numbering the tokens. So we will take the example of k-mers here, and we will just assign them any number or digit value. So we will go from the beginning, and the first one, ACC, will be a token 1. GTC will be a token with a number 2. ACC again will have 1. We've already assigned it a number, and we will continue like that. And once this is done, we actually end up in something like this. Let me show it in the next slide. That's better. So we see the token numbering, right? That's the numericalization we've seen. And now, if we put it like this into the neural network, we would make a mistake, because the neural network sees only the numbers, and it tries to search for patterns. And since we've assigned the numbers just randomly based on the order, it would the numbers don't really have any connections to each other. What I mean, for example, the first token is 1 and the second token is 2. So why are these numbers close? The network will think like, okay, this is the number 2 is higher than 1, so is it better, or something like this. It will try to find a pattern in the numbers based how close they are, for example, to each other. So this we don't want, because this is something that we introduced. It's not the nature of the data. This is basically our decision that we called it like it is. And so that's why we use one-hot encoding, which only takes these tokens that are numbered right now, and it will assign or translate them into a vector of zeros with one single number or digit 1. So our ACC will be translated into 1 and then into one-hot encoded vector, which contains 1 at the beginning and the rest are zeros. For the next one, we just move the one place further, and so on. So this is how we pre-process sequence data. And now when the network gets a vector of these zeros and 1, it will not assume that they are like there are some, or it cannot assume from the data that there are some connections or some similarities based on the value of the numbers. It will not assume that ATG is 6, so it's better or more important than an ACC, which is only 1. So this is how we treat the sequences. And also there are further processing or like transformations of the one-hot encoding. That one is called embedding, for example, and that we will have a look at tomorrow. So for now, we are fine. We are OK with our one-hot encoded vectors. We will use this in the example that comes soon. Now, let's have a look at genomic data and how CNN treats them, or in general, like sequence data, because we have seen images so far, and so we are used to having like a square filter that we apply over the image, and it extracts some visual features for us, right? But here we just have a sequence of letters, and what does it do, right? The convolutional neural network. So it's very similar. It also tries to learn or search for some patterns. So it, for example, tries to see if A is together with C and T, and what does it mean? So it also uses the positional information of the sequence. That's what is CNN good for. It's good for finding connections that are close to each other. So it tries to find what combinations of the letters are producing some kind of outcome. So what of them could be like a feature. And we will have a look at our first example. So again, as before, we can go to our GitHub, and we will use the example that is called number 5, CNN on G quadruplex and DN one-hot encoding. All right, so first we just import some libraries as always. Then here actually for you, if you will be using these notebooks later after the conference, there are sometimes again descriptions of the thing that we are talking about. So this you can have a look at later, just to remind yourself what it is, or just to get another example. We will skip it for now because we've already talked about it now. So we continue. We will first get our training data set. So we only download it, and then we can, well, we cannot see it here now, I think. Yeah, but if we run it, we would see it here. Anyways, we download our training data set, then we just load it from the files there, and then we process it. So as was mentioned, we will have a variable that's for the labels, and this goes through our data set, and it takes every positive example and assigns it the number 1. So we will have labels. Each of the sequence will have a label 1 or 0 if there is, which means 1 if there is a G quadruplex structure inside of the sequence. And then we just pre-process again, or pre-process, we just put our data set, training data set to list. Important thing for the processing, so we will define a dictionary. This is what we saw on the slides, and it's how we do the numericalization. So we simply put all our characters into a dictionary, and we assign them a numbered value, which is not really important what it will be, because it will be anyways translated into one-hot vectors later. And also we are using the ncar here. And we, for simplicity, we've decided to go with just not the k-mers as we saw in the pictures, but our tokens are only single characters. So we will put our dictionary in use, and we will apply it to the data set and to each sequence of the data set. And what comes out is basically what we can see here on the print. So this is just, we chose an example sequence that we will print for us. So it's a sample from the data, and we see that the letters got translated into numbers. So CCG is now 113. And we continue for the one-hot. So for the one-hot, we actually can use a function which TensorFlow made for us. So we will just call it from the TensorFlow library, the one-hot function. It only takes our data set, and then it takes the depth, which is the number of tokens that we have. So it's the length of the dictionary. And here we will just have a look at some prints of our data now. So our data set is 300,000 sequences. Each sequence is 200 long. And how the characters got translated. So we see that CCG went into 113, and then it went into these one-hot encoding vectors. So for 1, we are apparently using this one, and for 3 or G, we are using this vector. And that's it. That's how simple it is. Now, actually, I see I've opened an older version, so I'm sorry for that. I will just skip to newer version, and I will later fix this problem in the GitHub that stayed there for some reason. So don't worry if you cannot follow me with the correct notebook right now, but you can just look at the screen and have a look at the notebook later. So we just get back into the place where we were, right? So we have the characters numericalized and one-hot encoded. That's where we are. And we did this for the training dataset. Now we need to do this also for the test dataset. So we will again download it. We will pre-process it exactly the same as for our training. So we change our labels from just the words positive into 1 or negative into 0, so our network can understand. And again, we put it into one-hot encoding vectors, nothing new. Now, just so this works faster, we make our data set a bit smaller because 300,000 sequences is a lot, which is good. We want to have a good data set to have a good model later. But just so the notebook runs faster for you, we put this at less. But feel free to play with it. You can put it, you can just completely put this into the top and use all the data set when you play with it. Anyways, now we will go to our model. So we will just use some variables. So our sequence length, we know it's 200, and our number of channels corresponds to the length of the dictionary again. So it's 5, which is the number of our tokens. And this is like number of channels that we will go through. So actually our input doesn't look like it's not 1D. It's not like not 1D, but it's not letters ABC or ACTG, but it's the one-hot encoded vectors. So this is the length of the one-hot encoded vectors. And they all, like, each of the first position in the vector will be the first channel, second position in the vector will be the second channel, and so on. And now let's go to define our model. So it will be, again, a convolutional network. So we'll build a sequential model. We will use 2 convolutional layers following each other. We are not using max pooling just for simplicity. And we are using the ReLU activation as before. And just our filters have the size of 10. And our kernel size is 6. And so we have these 2 convolutional layers, then we flatten them, and then we stick dense layer on top of it. So it's actually even simpler neural network than we saw before. Then we have to compile it and assign a loss. Here we are using a sigmoid activation function because our last layer has only 1 neuron. So actually we don't have 10 classes like we saw for the images, for example, but we have just 1 output, not 10. And the 1 output will be close to 0 for negative and close to 1 for positive sample. So that's why we use a different activation. And then we just call model fit. So it's what we've already seen before, right? And we put data set, we put the labels, the name of the data of the variable data set. It's a bit mistaking, is it the word? Maybe because it's only the input of the layer, and the labels are what we expect the output to be. And we just start our training, and then we can follow the accuracy, the validation accuracy, how it looks, and then we evaluate our model using the test. part of our data set. And now we are just plotting here. So our evaluation of the data set on the test, sorry, not our evaluation of the model on the test set is here, and we can skip these cells. It's just for this plot. So we can see the training accuracy in blue, the validation accuracy in orange, and the testing metric, the testing accuracy in green. And the testing one is averaged. That's why it's here as a line, because there are no epochs when we are testing. So it's just one stable accuracy that is averaged through the whole data set. So we can see that it's quite okay, but we will try to work on it. We will come with another example that tries to improve this. So let's get back to our presentation. And we will. So right now we had this CNN model, and we are trying to use it to classify G-quadruplex sequences. And we will continue with this example, but we will try to introduce regularization. So we will have a look what this actually is. It connects closely with overfitting. Actually, it's the regularization is a group of methods that are trying to fight overfitting. Now, what is overfitting? We will find out very soon. You can so far guess from the picture. And we will have a look at some regularization methods. So actually, we have seen some of those already. We have seen data augmentation. And we have also heard mentions about making our model, or sorry, our dataset larger, which is also a method that helps us to fight overfitting. Let's finally find out what it is. So overfitting is like a state of model which is described or happens when our model learns the data too literally. So basically in this example, when we have just simple data that some value of time varies some numeric values here. And if the model overfits, it basically almost learn our examples by heart. Not necessarily learn them all, but something close to it. So it will find some features that are maybe not important for our class. For example, a deer on a grass with a forest in the background. So what we are classifying in the image is the deer, but because of some problems, for example, with the data set, our model can approach this problem with picking just, for example, the grass that the deer is standing on, and it sees, because our sample has a deer on the grass, it's easier enough to say, okay, I see grass, it's a deer. And if none of our other classes is on a grass, so we don't have any other examples that would actually want to use the grass as a feature, it's simple for our model to classify the images like this. Something that is, let's say, the opposite of overfitted is underfitted. So it's when our model generalizes too much. So it doesn't really learn features of our data set. It just approximates it very, very roughly. And we are aiming for something in between. So we want our model to generalize, to find the features that are important for the class that we are fitting on. So how we can notice that overfitting is happening in our training? So we can notice a high accuracy on the training data set. So when we start to train a model, we see that we are very, very successful, but if we are only checking this for training data set, then like it's a problem. So we are also using validation and test data set to see if our model just doesn't learn everything by heart or is not learning some weird features. So that's why we follow all these metrics. That's why we follow training, validation, or testing. So if we are very good on the training set, but not good on the validation or testing, mainly testing, because it was not used anywhere in the training, then it could be a sign that our model overfitted. How do we fight the overfitting? So one of the ways could be, for example, dropout. So it's a technique that we put, actually, I have split, okay, this slide is the slide that I want. So it's a technique that hides some of our neurons, let's say hide, and it gives a chance to the others. So let's imagine, let's look at the picture and imagine that the neurons that we hid or just somehow temporarily removed from the classifying, let's imagine that they contained the bad feature that we don't want. So imagine that the input of this network would be our deer on the grass, and the neurons that we hit learn to predict that grass means deer. So if we hide them and we don't allow them to influence the classification just for this step, just for this one image, then the network actually has to use the other neurons to tell us what it is, if it is a deer. And then it tells us its prediction, and we influence the, then we change the neurons and the weights. So we change the weights here to make the prediction better, right? So, but with dropout, we only change the weights that are connecting to the neurons that we used for the prediction. So all the grass neurons that are out for now, and we help the other neurons to find some feature that classifies deer. So this dropout forces all neurons to learn in this way. It's, however, used only during training, because during inference, during prediction, once our model is finished, and we, for example, go to the testing phase, we don't need the dropout anymore, because we are trying our model to perform the best, and it should already be trained. I have a bit mistakes in the slides here. However, let's have a look at how this works in more detail. So we start by choosing a dropout rate. This is how many neurons will be removed or dropped, hidden. And then at each stage of training, this is meaning, for example, for each batch, we remove or hide the neurons. This in practice means that these neurons and the connections, they are actually still there, even when we use dropout, but they will produce the number 0. So this neuron that is crossed out will put input 0 into the next neuron, which will be multiplied by its weight. So it doesn't matter what the weight is, it will just put 0. And so we hide these neurons, and then we calculate the output, as we said. So we let it predict the deer picture the best that it can. And then we propagate through the neurons and their connections how they should change to make the prediction better. And once this cycle is finished, we start another, for example, batch. So we start with another batch, and we then put these hidden neurons back to work, and we drop some different neurons, just randomly, for example, 20% of them. So now let's conclude and then have a look at our example. So since we are also coming to the end of our presentation, this will be our last few slides or our last example, and then we will end. So the conclusion of regularization. So we have seen dropout and we have seen data augmentation, and basically what regularization tries to do, it tries to introduce some additional knowledge to the model or to our training as a whole. So for example, data augmentation, we input our knowledge of the data, which means we know how to augment them correctly, and we change our training data set in the correct way. So it's some additional knowledge that we input to the training process. For example, another regularization that we can use is just make our data set bigger, but then we would have to get ourselves more data, which is usually difficult. Also, larger models, an example of overfitting would be that if we have a large model, then it might be so good in a way that it remembers all our data sets. So it remembers all the images, for example. So for example, let's imagine that it would have so many filters as is the number of our images. And then it can each filter can fit one image. So one filter will pick, for example, in the deer picture, it will pick some part that is very specific for this picture, and it will remember, when I see this deer picture, it has a weird ear. The deer has a weird ear, so I will classify this as a deer. And that's a problem. So, for example, if you use smaller data sets, they are a bit more motivated to generalize because they don't fit all the data inside them. So they have to find some feature if they want to be good in the training, which we want them to. Also, this whole regularization method or methods are used. Their main goal is to reduce the error of the testing dataset. So when we use them, we might not see that they help us with our training accuracy. They might even reduce the training accuracy lower. But we should see that they help us with the testing accuracy. And also they are not perfect, that they are not like some magical methods. They are not useful every time. But if we employ them in a good time, in a good moment, they can help us. So for example, if we have a small data set, we can employ them.
David, I'm sorry, could you speed it up a little?
Yes, of course. So we are going to the last example. So let's have a look at that. Yes, thank you for the note, Peter. So we will try to have a look at our regularization in practice. So we open our Colab notebook, and so we continue with the CNN as it was before, right? So we just do the same import. Here also you have dropout overfitting explained if you want to have a look at it again. It's how it was presented now. We do the same. We load and preprocess our data. So ACTG and the same data set. We can also hide this. So is this, and now we have our old model from the last slide. So we also skip this, right? And then now we get to model that uses the dropout. So it's very simple, actually. We just have a sequential model that, again, we include inside it some layers. And then we use the dropout. Actually, the notation for the code is we include it. It seems like we include another layer. And only thing what it does is that if we put in between of these convolutional layers is that it will drop some of the neurons, right? And it will allow only some of the neurons to put output into the next layer, as we've explained. So that's the model for now, we only included several dropout layers in between. And then we compile it again. Here we have the summary, so we can see the dropouts. We again just fit the model. And now actually let us proceed, because the end is near. Let us proceed to plotting the curves. So again, this is just the code for the plotting, so we can skip it. And let's have a look at the plot that it creates for us. So on the top, we have the validation, the training and validation accuracy, and the testing accuracy also for the first model, for the old model without dropout, and the lower layer is the model with dropout. So we see that, for example, the dropout model has a better evaluation or testing accuracy, a little bit better than the previous one, which is what we wanted. So okay, it worked, but what is the most important, or what is another important thing, is that if we look at the model, at the old model without dropout, we can see that the training and validation accuracy, it kind of differs a lot from the testing accuracy. And this is what the regularization helps us with. So it tries to improve the behavior on the training data set. So when we then evaluate on the testing data set, it gets closer. So here we can see that the training accuracy is much more closer to the evaluation. So it seems like it learned to generalize well. And just a meme at the end, and we can conclude, I believe. So let's.
Yes, thank you very much. Let's do the quick quiz question. I'll find it somewhere where it is. Yeah, not here. Sorry, too many Zoom windows open. So the polling is running now. Okay, and it seems that it was too easy.
Yeah, I expected so.
Okay, so David, can you comment a bit on it?
Yes, of course. As all of you know, so there is probably not much need to comment. Overfitting happens in all or most of the machine learning models because it's just the model, as we've explained, learned it exactly by heart, let's say, the data. Yeah, as Chris said, the audience overfit for the question. So I believe this is the end for now, and maybe Peter, you have some ending remarks, or should I do it?
I think me or Panos can do that for sure. So we didn't really finish.
Right, we didn't finish the day. That's the. But we can push the last part to tomorrow, I think. Best.
I think it's definitely a good idea. So just to sneak peek what will be there tomorrow. So today we have learned how to train model in Python in Colab and with TensorFlow. And the advantage of TensorFlow to other platforms like, I don't know, is that there exists something that is called TensorFlow JS. And you can take the train model as what we did. And oh, I don't want to see myself. I'll share the screen and show it to you. If you go to our GitHub repository, and you will, I hope there's the link somewhere. Yes. If you go to the web app, you can see that you will basically see some some classifier running on DNA sequences and some convolutional neural network doing classification, and it's not running somewhere on our server. It's actually running in your web browser. There is like no server included because it's all running in JavaScript. And we will show tomorrow and give you like the small guide how you want, if you want to do something like this, so how to do it. So that's something that what we will do tomorrow. Then tomorrow we will talk about the recurrent neural network. We will talk about explainability, about how to see why the neural network decided how it decided. And then finally, like most of the collabs we are doing here, we are doing very fast. So we want at the very end do some breakout sessions. So we will be in a small groups, which each led by some organizer, and you will be able like to work on your own pace and program your network. And for this, I would like to do some voting, like what could be, we need to prepare data set for it. So first of all, before anything, if you could post into the forum whether you would like the image data set or whether would you like some DNA sequence data set. So if you can post image or DNA into the forum. Okay, it seems very clear. So, okay, like from what I have seen, like DNA has the clear majority. So let's do the DNA. And for image, I would have some ideas. For DNA, I would probably need to think a bit deeper, but yeah. And we definitely will have the GradCam explanation.
Yeah, we have the GradCam.
Somebody's asking whether RNA would be the same, and
Same thing,
I would say, like, from the technical point of view, it's basically the same thing. Were there any questions during the last blog that it still?
One question that got kind of skipped was if dropout applies to filters in CNNs, which I guess, yes.
Filip, so I can answer. Yeah. So yeah, filters are just basically, you can basically imagine them as neurons. So yes, you can apply filters to you can apply dropout to filters. You can basically skip some filter or skip some part of filter during the training.
Okay, so let's see. I'm trying to think what data set we have ready, so we don't need to scramble to make a data set for tomorrow for DNA.
I think we can like decide it like after.
Okay, we can figure it out. Yeah.
Something nice. Okay, so thanks everybody for coming. Thank you for staying here for the whole 4 hours. I know it's really hard to stay awake. And thank you for all the questions. I'm really glad, like, we have excellent questions. We have excellent people like interacting through the Zoom chat. And I hope that like tomorrow it will be the same. I see people that are like sending ideas for the data set. Thanks for them. We definitely like consider it, but we will be looking for something that is honestly like small and nice.
And Petr, we can upload the first day the slides of the first day today, right? People are asking if the slides will be available because the GitHub page doesn't have the link to the slides. So.
Oh, definitely. No, definitely. I didn't realize it. I hope that we have corrected like both the mistakes in the notebooks that we have. Like
I think it's okay now.
And it should be okay now. If not, like let us know and we will do further corrections. Okay, and definitely like we can start tomorrow with question and answer session. So if you find any additional answers through the night, then
Okay.
we will answer it tomorrow. Okay, perfect.
Okay, thank you. Bye.
Thank you.